All right, so now this is our last lecture in Chapter 3. There's really no new material to cover, but I want to spend time going over some more of these concepts and solve application problems. Let's take a look at this first question right here. In a free body diagram for a particle, all forces that act on the particle must be shown. True or false? So this is definitely true. Everybody was spot on, right? So there you go. That's a good way to start. How about this one? In a free body diagram for a particle, all forces in the diagram must have known magnitudes and directions. All right, hopefully you were in. I saw you reach. Did you get in? Yeah. All right, you got in. Well, so why is this one not true? That's the point. You get a free body diagram and there's some unknowns in there. Typically, the direction is unknown or the magnitude is unknown. Some information's given, some information's missing. Get to it. Solve for the unknowns. All right? All right. Let's go with the next one. A continuous cable that passes over a frictionless pulley must have constant magnitude tension force throughout the cable. True or false? All right. So everybody's good. That's right. That's one of the themes about a frictionless pulley. The cable goes around it, and the tension in the cable is the same. Both systems support a mass of 5 kilograms. Both systems are made up of one, what would you call this object right there? A pulley, frictionless pulley. And what is it showing right up here? It's attached to the ceiling. It's supported by hopefully the bolts don't break or the weld doesn't break and it falls down, but it's supposed to stay rigidly attached up there to the ceiling. Okay, which system requires the least tension force to support the mass of 5 kilograms? System A or B, or they both require the same tension, or you need more information? How many people with a pen in front of them and a piece of paper in front of them actually did some doodling? You should have done some doodling, I think, to solve this problem, to analyze this problem. Engineering's not guessing. Engineering's analyzing. You can analyze this. I'm going to ask this again. What should you use to analyze and answer this question? Can you develop a free body diagram of this system A right here? What would it be? What would be the focus of the study? I would focus, well, if you do it right here, right? If you try a free body diagram of this pulley, what did you have to cut through? The support. All right. So if you do a free body diagram of the weight, the mass, it has the weight going down. What is the tension in the cable pulling it up? It's equal to the weight. Guess what this tension is that I'm going to have to pull down on is equal to, going around a frictionless pulley, the weight of the object. So if it's 5 kilogram force or 5 newtons or 5 pounds, then it's 5 pounds tension that I'm going to have to hold it, pull it. Okay? Let's do this one. Should I do a free body diagram around here? Sure. Then this is a support going to the middle of that pulley, and we know it's the weight coming down. We do a free body diagram around this pulley, and so now we knew that either the shaft or the cable holding that is coming down with the weight W. But I have 2 cables coming up, do I not? You cut right there and cut right there. And this is a cable going around a pulley. If it's in tension T, it's pulling up with tension T, pulling up with tension T. True or false? So if I do the sum of the forces in the Y for this one equal to 0, this one was so easy. It was sum of the forces in the Y equal to 0, and I concluded that the tension force in the cable is equal to the weight. Here I conclude that 2 times the tension in the cable is equal to the weight, or the tension in the cable is half the weight. Half the weight. Let's say you're a skeptic. Is that enough to convince you? Is that enough analysis in that? Yeah. So, which is the best answer? The minimum or the least tension force will be with case B. Do you think we're over 50% correct? Close to 100% correct? 46% correct. All right. How about before? We were 22% correct. At least some of us moved in the right direction. But there were 50. How many people participated that time? 50. So, unfortunately, some people dropped out. Let me see. Okay, we went from 11 to 17 correct, but we went down in the number of votes. Right. All right. Well, I moved on to the next question. Let's close this. Okay. Here we go. Question. As the angle theta increases, what is this angle theta? Right there. So you're going to have a support to the ceiling, a support to the ceiling, a support to the ceiling in all 3 cases, A, B, and C. You have the same mass, the same frictionless, weightless pulley. And what are you doing here? You're pulling off at an angle theta. Instead of theta being 0 degrees, maybe theta is 30 or 40 or 50 degrees, something. It's not 0, right? Okay. Okay, let's now get back to the question. As the angle theta increases from 0 up, the pulley in the cable system will look more like either case A or case B or case C. Or you need more information? All right, everybody's in. Let's take a look. Yeah, why does it look like that? Why is A the more proper look? And so what he's saying is you're getting a component of the pull on the end of the cable in the X as well as the lift in the Y. And when you do a free body diagram of that pulley at A, this pulley, then you'll have the weight going down, which you're trying to support or lift. You'll have a force at some angle theta, the tension force, and then you'll also have a tension force. Now, if this tension force went straight up, as in case B, all right, what's to balance the X component of this force? Nothing. You can't get some of the forces in the X equal to 0. Nobody was fooled by case C, were they? No. But this one. Now, this one you may illustrate in an illustration, but you know, okay, they're taking some artistic liberties here. But in reality, if I start pulling, increasing theta, it's this object's going to move a little over, and so that this pivot will be over like that. See? True? All right, very good. Whew, this is an easy one. A mass of 50 pounds sits on a table. Determine the magnitude of the contact force between the mass and the table. So if I said I'm going to do a free body diagram around this 50-pound object sitting on the table, I have got to come in and I have to cut. Should I cut through the table and then the air underneath the table and then come up like that? No, you're going to be left with, well, how do I handle this cut through the table? Okay, how about if I cut through the air and I cut through the leg and then I cut through the leg? Well, that's probably not smart. I mean, we have to isolate the focus of the study. That's one of the great themes of this chapter, actually of the whole class. Free body diagram. Isolated body diagram. Here it's just a particle. It's the simplest you got. So what you're going to do is, I'm belaboring maybe a point, you got to cut right between the block, the bottom of the block, and the table. And when you cut right there, you just have now the weight coming down. And what do you have going up? The contact force. It's sitting on the table. The table's pushing back with the contact force. And when you do the sum of the forces in the y, guess what the contact force equals? The weight of 50 pounds. This was not a hard question. It's 50 pounds. Or 50 pounds. I don't know why I'm getting other answers. I don't know. Okay. Well, that was supposed to be a confidence builder. As the angle theta increases, the tension force in the cable will, what will F do to hold the same mass? Will it increase, decrease, remain unchanged, or you need more information? Now, we already talked about, you can think about this moving over a little bit. So you have to think of this starts at theta is equal to 0 and this other side straight up and down, okay? But we already talked about that. So we're out of time. Hopefully everybody's in. Now, I think I had a little discussion, and as you start to increase the angle theta, we all agreed that this is a better representation. Well then, Professor, why didn't you put that representation out there? And I tried to explain that sometimes things are done with a little artistic abilities, right? So if I take this illustration, copy it, I jump over to the problem, not that problem, this problem that we're solving, right? And I do edit, paste, and I say, you know what, that's the better illustration as theta increases. True? We just talked about that. And I asked the same question, would I get 100% correct? Probably not, I don't know. But in the interest of time, let me grade this. But you had to, and I think to answer this question correctly, you had to do that in your mind. You had to say, I know that the orientation, the distance between this location right here, coming down, let me just do this, and that location starts to increase as theta increases. All right. Well, what does the tension cable do? It goes up, right? And that's a very common thing to do. So if you're trying to lift something, you know, exert a force upward on something, and you're going to do it by having a very, something like a cable in tension, and that cable has a large theta, so to speak, you're going to need a very large tension for the weight that you're trying to lift. You will need extremely large. All right. All right. On the springs. All right. Two springs are arranged in series. This word trips me up. It's parallel or series. It's aunts and uncles. It's left hand, right hand. You know, these things like what is parallel, what is series? Are these two springs in series as shown? Yes. All right, good. So we got two springs in series. The stiffness of one and the stiffness of the other spring are given. If 300 Newton force is applied, what is the compression of the spring system? Like, how much does this location move to compress in units of centimeters? Ed will take it as not a multiple choice, but a numeric. And how much time should we give? 3 minutes. There you go. All right, so let's do this. Let me ask you this. If I didn't have this side over here, if that was missing, right, and I have to maybe hold it back with the force, what would be the magnitude of that force that holds this back? If 300 newtons is applied to the left side of that spring, what has to be applied to the right side of the spring? 300 newtons. Okay, so guess what this spring is doing? It's pushing back on the first spring with a force of 300 newtons. And this spring is pushing over with a force of 300 newtons. What's the support, the wall doing on the second spring over here? Is it pulling with 300 newtons? Does it have zero force? No. It is a contact between this spring and the wall, and the wall is pushing back on that spring with a force of 300 newtons to keep it in equilibrium. True? Okay, so what happens is like the force is transmitted through this. Let's say I took this first spring all by itself, I put it against a rigid wall, and I said, what is going to be the compression? Maybe you like the compression, you use either a symbol C for compression, or stretch, you use a symbol S. What was Hooke's law? F equal to Ks, or F equal to Kc. If you're compressing it or stretching it, it's this, or you worry about the negative sign. Either way. Okay. So what is going to be the compression distance if I put a 300 Newton force on only this spring, which is rigidly supported? Will it be the magnitude of the force divided by the stiffness of the spring? And what do you calculate for that one? 300 Newton divided by 100 Newton per centimeter. And so you get how much? 3 centimeter compression. How many people did that? Just show of hands. Quite a few. Then you say, you know what? This spring right here is going to have the same force. How much force? 300. You know what? I'm going to re-ask this question. I'm going to give you a little more time. I want to see if you now can solve that problem with a little more hints and guidance. All right. So 4.2 is the correct answer. Addition. All right. Let's see how you did before I gave a little hint. Actually, not too bad. So we had 23 correct, but then a little more discussion was able to get 42 correct. So why are we going back and we're jumping around? We're going to do some spring problems. Then I'll switch in and do some cable pulley problem so that you'll forget a little bit about springs. And then we'll do some smooth contact surface problem. And then we'll jump back and do a spring problem, a pulley problem, and guess what? And then the students finally, I think, start to grasp. Like, I got it now. Let's do this one. So we have a 50-pound ball sits on a smooth surface that's inclined at a 25-degree inclination. So what does this word smooth mean? There's no friction there. A spring restrains the ball. Here's a spring. It's attached to this end, and it's attached to the ball right there. Okay. What is the magnitude of the contact force between the ball and the surface? And the ball is 50 pounds, so I want the contact force in units of pounds. All right? So I'm going to give you enough time to solve it. Numeric input. We'll give a good 4 minutes. How do you solve this problem? What's the first thing you want to do? Focus on something, cut it free, make a free particle, body diagram. So if I need to focus on probably the 50-pound ball, so I'm going to cut through air. Air exerts no force on the ball. But then I've got to either cut through the plate, bad idea, or cut through the contact between the ball and the plate. And it was smooth, so there's only a normal force between the ball and the plate. Later we'll get to a chapter we deal with friction. Then you have a tangential force as well with friction, but not now. Contact force is only perpendicular. So then we come up here, and are we going to have to cut through that spring? Yeah. Yep. What about, hell, let's include the spring. No, you cut through the restraint then. No, you can't do that. That's not going to help. So this is... When I isolate it, I come down to a particle. Don't forget W. What's that? The weight of the ball. And then don't forget the contact. Now, this is a little tricky. The contact is perpendicular to the slope of the plate. All right? The spring is a little easier. If I draw horizontal, this is horizontal. What's the angle here for the spring pulling up? 25. So maybe what I do is I put in a coordinate system to help me a little bit. Let's call this X and Y. And then we'll put in a force for the spring. Force in the spring, which I don't know what it is yet. It's unknown force, but it's on the free body diagram. And I'm going to probably give its orientation by this angle, which is what? 25 degrees. All right, so now let's get the other force in there, which is a contact force. Now you could put the contact force like that. True? And then you've got to figure out an angle for that contact force. Is this side 25 or that side 25? Side A or side B is 25 degrees. Clicker question. We'll come back and grade that one. One of those two angles, A or B, is 25 degrees. This force right here is my contact force supporting or reacting to the bottom of the ball. And so a lot of you followed that one, so we do have a lot of correct responses. This is the 25 degrees, isn't it? This is the 25 degrees. How do people work that out in their mind? Usually I kind of rotate it. Is that how you do it? Do you rotate it in your mind? Yeah, that's a good way of doing it. All right, now you can also take that force and you can displace it like this, such that the base is at the point, right? And it's maybe conceptually a little easier, right? The force. And then what is the angle? Is this the angle 25? Or is this the angle 25? Let's take a look here. We had this straight line. The force, we're just moving it up. And I need to get my angles correct. Isn't this the 25? Right? Okay, so that's our 25. I think it's a little easier if you just have all of your forces coming away from the point. I know compression forces or other forces, and if you're really good at it, fine. Work with that one going into the point, free body diagram. Now, I would do an equilibrium. I had the sum of the forces in the x must equal to 0. That gives me one equation with, I have Fs times cosine 25. Is that right? For the spring force. Equal to the force contact times cosine 25. Is this true, or did I write the sum of the forces in the x correct? The sine. Sine. Very good. Sine of 25. True? And then we'll do the sum of the forces in the y equal to 0. We're going to have Fs times the sine of 25 plus Fc times the cosine of 25 equal to the weight down. Thumbs up if you like that. Is that okay? All right. At this point, can I rephrase the question and see what you get for a numeric answer? Let's repeat the question. Let's do it again. What is the magnitude of the contact force between the ball and the surface? And it's back to numeric. And away we go. And let's get 2 minutes, but no more. 2 minutes. So how many people said, look, I have two unknowns, F of C, which I'm looking for, and F of S. I don't know the force in the spring, do I? But if I take the first equation, I can express F of S as F of C times the sine of 25 divided by the cosine of 25. I then can take that and substitute it, so I modify the last equation, or the sum of the forces in the y equation, such that you get F of S times the sine of 25 plus F of C, F of, you substitute this right here for F of S, and you pick up F of C, which is the sine of 25 times the sine 25 divided by the cosine 25 plus the cosine 25, all of that equal to W. And so F of C is equal to W divided by, you can put the sine of 25 times the tangent 25 plus the cos of 25. How many people did that? And you then sat on your calculator, crunched it, and you were able to get, so 45.3. Thumbs up. Good, 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 good. Let's press forward. Oh, back to pulleys. Which system requires the least tension force? System A, B, or C to hold up this, what is it? How many kilogram mass? 90? 90 kilograms. So what would be the helpful free body diagram to solve this problem? Free body diagram maybe around this pulley? Would that help? Sure. Okay, if you do that, you find the tension, tension, weight, the tension, tension, weight, tension, tension, weight. True or false? Is there any difference between the free body diagrams of the bottom pulley and any of these illustrations? But you're saying to yourself, something's dramatically different. You're pulling up here, different. Something's different. Something's very different. Well, let's do a free body diagram of that pulley, the top pulley. Okay, if you do a free body diagram of the top pulley, I have down with tension force. And what do you think the support's going to have to do? I had to cut through the support. It has to do something. It's going to pull up. All right, let's go to this one. This is kind of the extreme. All right, so I have my free body diagram of that top pulley. I have tension down and tension down, or maybe I should use F instead of T. F and F. Maybe this is F and F. Okay, so I'm consistent. Okay, how am I going to hold that in equilibrium? What's that support going to have to do? True? And if you think about maybe the distance between here and here, that support may bend a little bit. Hey, that's the whole class of solid mechanics. Leave something for the next class, professor. Let's not learn everything in one class. Okay? Let's leave that for another class. Internal force and that bending on that component. All right. So, but it's going to have a net force to hold it over. It's going to have to kind of pull it back and pull it up. Where this support right here, what did it have to do? Just had to pull it up. Okay, then we go do this one just for completeness. Free body diagram, we have the force tension down, we have a force tension off to this direction, and you're going to have something that's like that. It'll have some significant lifting as well as some holding back in the X. Did that make sense? So which one has the least tension force? It's all on the first or the lowest pulley that really helps you. And the best answer is, don't they all require the same tension force? Let's grade it. Man, I thought I mastered pulleys and cables before this lecture. All right, let's press forward. Springs. Hey, didn't you request a spring problem?
I
All springs in this problem are identical. What do you mean by identical? They have the same unstretched length. They have the spring stiffness. They're identical springs. Three identical springs are arranged in parallel. Are these in parallel or series? They're parallel. Good. Force of 100 newtons is used to compress each spring, or the springs, by 0.4 centimeter. What is this compression distance right here? 0.4 centimeters. What is the stiffness of each spring? What is its stiffness? What was the symbol for our stiffness for springs? The letter K. K. All right, and so the units that makes most sense are newtons per centimeter. True? Is that what you suggested? Newtons per centimeter. We want our answer in newtons per centimeter. All right. Anyway, if you want, we could do a free body diagram of this junction point right here. And you would have 100 Newton applied, and you would have three forces that are all the same, each in the spring, Fs, Fs, F, because they have the same compression, the same stiffness, the same unstretched length. They're going to have the same force. So guess what each force has in it? 100 newtons divided by 3. So it's like it carries 33.3, 33.3, 33.3, right? Newtons of load in the spring. And once you figure that out, then what you do is you say, well, what's Hooke's law again? F of S is equal to K times the compression distance. And so K was 100 newtons divided by 3 divided by 0.4 centimeters. Does that give me the right units of Newton per centimeter? Sure. And then we take a look at our number, and we get an answer of 83.3. True? Very good. I think, are some of you bored? Should I go faster? No? Oh no, I can't do this. There's too many of these problems. I got to continue on. Forget it. Do you want to do a ball with the spring at an angle? Yes or no? All right, let's blow it past it. But you need to be able to solve. And guess what? You can compare systems with 3 springs. Is this parallel or series? With systems of 4 springs, a parallel or series? I can't remember. Oh, man. Let's do this last one. All right, numerically, what is the tension force in pounds needed to lift a 50-pound crate? It's a numeric, and all you're going to get all right, let's grade it. Have we not done this before? Have we not done it? How many people said, oh, come on. Get some original problem here, huh? Somebody says, well, what about this slope right here? What about it? It's going to put a lot of stress on this member supporting your pulley, but guess what? It's irrelevant. You may break up here to support because it has to be in shear, but down here, what about this angle, Professor? You just got to get an answer. And so sometimes we neglect little angles like that. It maybe make the pulley way down here so the angle is less severe. True? But if you neglect that little bit of angle, it's 25 to lift 50. So that's the right response. Okay, fine. I'm tired. Do you want to do this one? Okay, no, I don't. If I have time, I'll come back. I got to solve this problem, then I got to come back and solve the homework problem. I'm not a hustle here, sorry. So the crate is supported by cables. How many cables do you see? There's really 3. Let's call this a rod or a bar. It's just, connecting. That's not going to be a unique cable. So the cable would be a cable going from A to D. Here's point A, there's point D. A cable from A to C, and from A to B, A to B. Those are our 3 cables. Okay. It's really hard to show, but it's rigidly attached at B, rigidly attached at A, rigidly attached at D. That's the notation. I mean, it's fixed. Those points are fixed. And all right. Likewise, you can see the location of each of the points. If somebody said, okay, what's the location of point A in the coordinate system X, Y, and Z? Where is A? At 0, 0, 0. At the origin. That's nice. That's convenient. Okay, where is, so maybe we write that down. The notation, the A is at 0, 0, 0 units of meters, right? Okay. What about the location of B? 2.500 meters. How about the location of C? 0, negative 2, 0 in meters. How about the location of D? Negative 2, very good. Positive 2, positive 1 in meters. So we get, there's a lot of information. It's hard sometimes. Some students will really struggle. Like, I don't get where the location of D is. Okay, if you don't, talk to your friend or neighbor or go to tutoring or visit me in office hours. Okay? You have to be able to get the locations in 3D. Some people, they get it right away. It's not hard at all. Probably 95% of the class. Easy. All right. The maximum tension in any cable is 3 kilonewtons. Why? What happens if I exceed it? It may break and the system fails. Okay, so that's our maximum tension. Determine the maximum mass of the crate that's being lifted. Here's our crate. So what is the mass maximum? What is the maximum mass? Let's just call it M. Now, how would we solve this problem? Well, we internally know that the weight that's in the cable pulling down from A to help support the crate is the mass, or the weight of the crate, which is M times G. Okay, now this is the maximum tension in our cable. Any of those cables could be reached first. All right, so, yes?
It says, it already gives us the amount of weight for the crate.
No, it's the maximum tension in this cable, or that cable. And let's continue on. So, well, this problem is begging to isolate a point, do a free body diagram. The most logical looks at point A because it's not rigidly supported. The other points are rigidly supported or fixed. It's so if I do a free body diagram, it's good to try and do these once or twice in your life. In 3D, it's a little hard, but what we get is we have the tension or the force going out to B. We have the force or the tension going out to D. We have the force going out to C. And we have the weight going down, and all of those are three-dimensional vectors. Did I leave anything off? Did I miss any force or weight or contact or whatever on my free body diagram? Okay, I think there's only these 4. Let's do this. Can you express weight as a vector in 3D? Well, it'll be the mass times G, but I'm really interested in something I, something J, something K. What is it going to be for a weight vector? It'll be 0I, 0J, negative 1 in the K. Does that make sense? The magnitude is mg. It's sitting out front. All right. Now, what about the force in vector, I don't know, B? Well, it'll be the tension in the cable going between A and B. Maybe we just call that the tension in the cable B. But then I have a actual, multiply it by what? Little unit vector. And the unit vector gives me the right direction. So what would be the unit vector going from A to B? It would be 1I, 0J, 0K. All right. Once I get all 4 of these vectors described in vector notation, then I'll do the sum of the forces equal to 0, and I'll get 3 algebraic equations for the x, y, and z direction. But what about the force going to C? That's equal to the tension in the cable C times a unit vector going from A to C. What is that unit vector going from A to C? All right. So 0 in the I, minus 1 in the J and 0 in the K. And that minus sign, we need that, right? Okay. Now the hard one is the force vector going off to D, which is the tension in the cable going to D, but I need that unit vector. That unit vector goes from A to D, and that will require a little work. How do I get the unit vector from A to D? It'll be that displacement vector going from A to D, which is the position vector D minus position vector A. And luckily we have all of our coordinates of D and all our coordinates of A. It's almost too easy. It just says, look it, you need to move -2 in the I, -2 meters in the I. You need to move +2 meters in the J. That's as a plus, not a comma. And you need to move 1 meter up in the K. All of this as a meter length. I'm sorry, I messed that up notationally. I'm trying to get unit vector from A to D. I need to get the displacement vector from A to D and then normalize it, divide by the displacement vector from A to D. True. The magnitude. And the magnitude you just calculated is? The magnitude of the displacement from A to D is? I just heard you call it out. 3. So now the unit vector is, did I do this okay? Okay. Now the unit vector, I can finally express it right in here to save space. It'll be -2/3 in the I, 2/3 in the J, and 1/3 in the K. And it's good every now and then to pause, look for any error, make sure we agree. Does it look good? Look good? Okay. All right. Now, that was the hard part. Now I have to unfortunately scroll down. So I'll have to get a little more room on my paper. And we'll do the sum of the forces in the x equal to 0. When you do the sum of the forces in the x equal to 0, what do we get? We're going to get an equation that says TB minus 2/3 TD is equal to 0. All you do is pick up this component and that component. Those are only two that have anything in the x. All right, let's do the sum of the forces in the y equal to 0. And the equation that we get is we're going to get -TC plus 2/3 TD equal to 0. You just pick up this component and that component. And then do the sum of the forces in the not y, z. That's equal to 0. All right, so we're going to get the negative of the weight, which is mg. If you want, let's leave it as mg. And we'll put plus 1/3 TD equal to 0. So we just pick up this component and that component, because the others have 0 in the K, or in the Z direction. Do you like these 3 equations for equilibrium? All right, so how do we solve this problem? We want to calculate if so maybe you want to do this. You say, okay, I'll pick, and I'll say the tension in D is my maximum tension, which was 3 kilonewton. True? So if that's true, if this is true, if that's true, then what we find from this equation is that the tension in B is equal to 2/3 of TD, which is 2/3 of 3 kilonewtons, 2 kilonewton. This is okay, not breaking. All right, let's go to the next one. Let's check this one. Then we'll find that tension in C is equal to 2/3 of the tension in D. It's also equal to 2 kilonewton, and it's okay. It doesn't exceed the maximum. And then what we do is we come over here, we find the maximum mass is equal to 1/3 of the tension in D divided by G. And so the tension in D, let's do it, 1/3 of 3 kilonewtons divided by 9.81 meters per second squared. And then what is a kilo is 1,000. Don't mess up your units. And then what is a newton is a kilogram meter per second squared. And so that will give us a mass. Somebody have a calculator? They want to run that for me? 102 kilogram. Now, somebody says, that was a lucky guess. Fine. Let's go over here. Let's pick, I don't know, the tension in B to equal the 3 kilonewton and see if that'll work. Okay, if you pick the tension in B to be 3 kilonewton, then you have to calculate from this first equation, you have to calculate that TD is 3/2 of 3 kilonewton. Guess what? That's 9/2, that's 4.5 kilonewton. This will not work. Does that make sense? So it's like, it seems like that's not very elegant. Does it work? You know, just check, pick one and try it. Okay, if TD is at the limit, then the other one, TB and TC, are below the limit. They're okay. That looks good. Try TB at the limit. Oh, TB exceeds it. That's not going to work. And you can see the same thing. If you pick TC at the limit, it would also have TD exceed it. So there's the solution to that nasty problem. Okay, are you asking about B or? Yeah, their unit vector, and from A to B is purely in the X. And so it's just 0, 1, 0, 0. And then from A to C is purely in the negative Y. Well, they're all unit vectors. This is a unit vector, that's a unit vector, that's a unit vector, and that's a unit vector. Yeah. It's just, if this one is a unit vector down in the negative Z, this is in the positive X, this is in the negative Y, and this is off at some angle in the quadrant over there. Yep. All right, so let's solve this problem. What we have is a ceiling, we have a rigid attachment, and from that we have a cable coming down, which connects to the middle of a pulley. And around that pulley is a cable that is pulled with a force F. So that's the tension in our cable that goes around. And down here is a crate. It has a weight. And this weight is 20 pounds. And you want to hoist it. Either you want to support it or you want to lift it at uniform velocity. You'll have to exert the same tension, because you're not changing the state of motion of C. All right, so there's some geometry given. This is what, 20 degrees? And then this angle is unknown angle theta. And we have F. All right, let's put in some locations. So this is location A, location B, location C, and then location D. All right. So the question is to solve for that, find that angle theta, as well as find the tension in the cable that goes from A to B. Object at C is a weight of 20 pounds. Can you tell me what F has to be? 20 pounds. Continuous through that cable around that frictionless pulley. All right, so we want to solve for the tension in this cable, A to B, and this angle theta. All right, what are we going to do? How are we going to analyze this problem? Statics. The refrain in statics is get a free-body diagram that's going to reveal how these unknowns are interrelated when you do the equilibrium equation. So you're going to do it up here around B. No, you got to cut through the ceiling. You already did it around the weight, so let's do it around the only thing that makes sense, which is our pulley. So if we do a free body diagram, I know it's a point diagram, around our pulley at A, what do we have? We have going off is the tension in the cable A to B. That's one of our unknowns, because we had to cut right through there. And just from geometry, if this is straight up and this is straight over like this, a little coordinate system, this is straight up. What is this angle right here? That's our 20 degrees. Very good. Okay, let's continue on. We're going to have a force going down. What is that? That's our weight. And then we're going to have this going down, which is our F, which we just concluded was our weight. Okay. This angle right here is angle theta. So let's just get rid of that and just call it weight. The weight. Makes sense? All right, so at this free body diagram, I kind of look around and I say, hey, this is my unknown. That's one of my unknowns. And this is another unknown. I'm glad I don't have more than two unknowns, because guess how many linearly independent equations I get for equilibrium? Two. Some of the forces in X, some of the forces in the Y. So for equilibrium, some of the forces in X must equal to 0. We decompose it, and we get the tension in A to B times the sine of 20. We'll push it in the negative X, and in the positive X, we'll get the weight of the crate, which is the tension pulley, or in the cable, times sine of theta. True or false? Did it look good? Thumbs up, please. I know it's a long time, but you're good? Stay with me, please. Sum of the forces in the Y equal to 0. We're going to get TAB times the cosine of, not 30, 20 degrees. And the weight plus the weight times cosine of theta. Look good? Two equations, two unknowns. So how do I solve this problem? Make it one equation with one unknown if you can. So typically they'll grab this one and say, which one do you want to eliminate? You either choose to eliminate theta or TAB. Which one do you think would be to get rid of, eliminate? TAB, after you solve a few of these, believe me, I've chased my tail so many times solving statics problems, it's not funny. But you want to write TAB is equal to W sine of theta divided by sine of 20 degrees. Substitute that in here in the second equation. So we rewrite our second equation, and we'll get that the W times the sine of theta times divide by the tangent of 20 degrees equal to W times 1 plus the cosine of theta. Did I do the math okay? Can I cancel W from both sides? All right, well, this is not a very pretty equation, but I have the sine of theta is equal to 1 plus the cosine of theta. You know, or this equation has to be true. So what I can do, and I encourage you to do this by hand, as well as get that sophisticated, high-priced calculator of yours and learn how to use it. Because your calculator solved this problem for you if you know what's going on. So what I did was I put this like this. I said, well, the tangent of 20 degrees is equal to the sine of theta divided by 1 plus the cosine of theta. And then I said, okay, well, what is the tangent of 20 degrees? It's 0.36397. And so by hand, and it's good to solve a problem or two like this by hand, I said I'm going to pick a theta, and then I'm going to calculate the sine of theta divided by 1 plus the cosine of theta, and then I'm going to just keep on marching until I find a theta that makes it equal to 0.36397. That's what your calculator is going to do. And so let's pick a 10 degrees. If you pick 10 degrees, sine of 10 degrees divided by 1 plus the cosine of 10 degrees comes in at 0.0875. Does that equal 0.36397? No. Keep going. How about 20 degrees? If you pick it, 0.1763. Professor, did you really spend time today running these numbers by hand? Yes. Do I expect all the students in this class to be able to do that? Yes. Yes. On an exam? Yes. Yes. Am I broadcasting types of things you need to be prepared for? Yes. All right. 30 degrees, if you put in 30, it's 0.2679. That's not equal. So you keep going. 40 degrees, and lo and behold, 0.36397, and it just goes spot on. And you say, I probably would have had a mathematician friend to work this out with some trigonometric identities. Remember that class I almost didn't pass? Called, pre-calculus or something? They made you do all these things where you manipulate on down and continue to work. But anyway, this is the answer for theta. You don't need to really go any further. You got it. Once I have that, I go back to my other equation. TAB was equal to the weight times the sine of 20 degrees divided by sine of theta, divided by the sine of 20 degrees. TAB, or TAB, whatever it is equal to 37.6 pounds. All right? You're free to go. Thank you for your attention.